In this lesson, we'll look at calculations to determine the percentage purity of a sample. Oftentimes, one of the reasons that the percentage yield of a reaction is not 100% is because of the reactants that we're using in the experiment are not 100% pure. We can study reactants and samples in order to determine their purity. Just to give this some context, let's think of a sample of silver nitrate, for example. When we take a sample of silver nitrate, that is 10 grams, when we're doing our calculations, we often are assuming that the sample is 100% pure, meaning that the entire sample is the silver nitrate. In a case where we have an impure sample of silver nitrate, it might be possible that 8 grams out of the 10 are actually pure, and the rest are impure. So there could be 2 grams of impurities in this particular sample. If there are 2 grams of impurities in a 10-gram sample, that means that the sample is 80% pure. Because as we've practiced time and time again, the percentage is the part over the whole. So in this case, the part that's pure, the 8 grams, over the entire sample, the 10 grams, times 100 will give us the percentage purity. Now when we're doing stoichiometric calculations with this, we're going to be using terms such as sample size, which is the size of the original impure sample. The percentage purity is what's going to describe the portion of the sample that is pure as a percentage. And the theoretical mass is something that we're going to calculate. Much like when we do percentage yield problems and we calculate a theoretical yield, we're going to calculate a theoretical mass for the pure portion of the sample. It's best to see this in an example, so we'll do that in a moment. Now, one thing to keep in mind is where this comes into play in the real world. Ores are naturally occurring rock that contain metals. And so when miners are working and collecting metal, they're not often collecting pure metal. They're collecting ores upon which the metal can be extracted. The percent purity of the ore is going to help to decide whether or not a particular area is worth mining. If there's a low percentage purity of the ore, then it's not going to make sense to do the mining. We use chemistry in order to determine the percentage purity of the ore, and we study it in a lab, and then the miners will decide whether or not they should go and mine a particular area. Let's do an example. Iron pyrite, FeS2, is known as fool's gold because it looks similar to gold. Suppose we have a 13.9 gram sample of impure iron pyrite that we heat in air to produce iron 3 oxide and sulfur dioxide. If we obtain 8.02 grams of iron 3 oxide, what was the percentage of the iron pyrite in the original sample? Okay, so what we have here, just to visualize this, we have this 13.9 gram sample of fool's gold, and you may have seen this before in shops. And we want to know what percent of this is actually FeS2. And the way that we do that is we study a 13.9 gram sample of FeS2, and we react it in air. We heat it in air, and anytime we're heating something in air, it's going to react with oxygen. And we're producing iron 3 oxide, which is Fe2O3, and sulfur dioxide. To balance this, we need the coefficients 4, 11, 2, and 8. Now we react this 13.9 gram sample, and what we end up producing is 8.02 grams of pure rust. And so what we need to do is calculate what we refer to as the theoretical mass. And the theoretical mass is going to be the mass of the FeS2 that is needed to actually produce this amount of Fe2O3. So once we can figure out the amount that was needed to produce the 8.02 grams, then we know the mass of the FeS2 in our original impure sample. This is called the theoretical mass because we are making an assumption here that every single last bit of the FeS2 is converted into the Fe2O3. So it is, in theory, the amount that has reacted. Now to find this theoretical mass, it is a regular stoichiometry problem. So we are going to find the moles of the iron 3 oxide by dividing by the molar mass, which is 159.7. And we find that it's 0.05022 moles. So that's step 1. Step 2, we are going to apply the ratio to find the moles of FeS2 that this was produced from. And we do that by taking the 0.05022 and multiplying it by 2 because it's a 2-to-4 ratio. And that gives us 0.10. And step 3, we're going to find the mass of FeS2. So this is the moles of FeS2. To find the mass of FeS2, we need to multiply by the molar mass. And the molar mass is 119.99. So that gives us a mass of 12.05 grams. So what this means, this theoretical mass that I've calculated, that's the mass of the Fe2S2 that was needed in order to produce the 8.02 grams of the iron 3 oxide. So if we're assuming that this reaction has gone with 100% yield, what this means is that 12.05 grams of my original impure sample is FeS2. So from this data, I can now calculate the percentage purity. Okay, and in this case, it is 86.7%. So the fool's gold was 86.7% pure in FeS2.